So I hope you can see the screen. I guess I'll have to increase the size a bit. Okay. So as you know, like this week's material is about summarization and text classification kind of things. So once again, because these topics are slightly more practical based, so we'll be going through a simple example of text classification, and we will also look at how to do it using PyTorch. So if you do not know, PyTorch is a library based on Python that is used for deep learning applications these days. So they have a lot of modules and other kind of codes for running deep learning models, and we'll see the simplest version of one such model. And the task that we are going to discuss today is sentiment analysis. So sentiment analysis is one form of um, text classification. The idea is that there are a lot of text which conveys a sentiment. For example, you can think of movie reviews. So movie reviews can be either having positive sentiment or negative sentiment, like whether the review describes something good about the movie, then it will be positive, and if it is something not so good, then it will be negative. So, and like sentiment analysis is done for mostly these kind of things like movie reviews or product reviews on Amazon and so on, like these kind of things. So we'll be discussing sentiment analysis, and I have prepared two parts regarding this. So the first part is the most basic rudimentary form of sentiment analysis using like very simple PyTorch modules. And if we get time, we'll discuss slightly more advanced concepts regarding this task. Okay, so let's look at what we have. So we are going to understand, like as you know, IMDb is a popular movie review and like movie details website. So they have reviews about movies and ratings and so on. And there is a popular IMDb data set which is used for sentiment classification. So we will be doing that one. We'll be using that data set over here. So before we go into the data set and other things, let us look at the neural network architecture we'll be using. So as you know, um, like one simple way of applying deep learning for sentiment analysis would be something like, say you have a sentence which describes the comment of the user, and then you can construct a feature vector out of that sentence like the ways we have done in previous tasks. So that feature vector can be constructed manually. You can decide on some handcrafted features, and then you get a fixed dimensional vector that represents that sentence. And then the simplest neural network is known as a feed forward or linear network, where it's just like a simple matrix multiplication, where like that vector is converted into another vector which has the output dimension as the number of classes. So in this case, we are talking about simple sentiment analysis. So like the sentiment is going to be either 0 or 1. So the output neuron or like the output features will be 1. Like there will be only one output feature, and based on the value of that feature, like we get, suppose you have a feature vector that represents the sentence, and that feature vector is of length 100. Okay, so then you can pass it through a 100 cross 1 matrix, like you can multiply it with a 100 cross 1 matrix, and then the resultant matrix will be of 1 cross 1 shape. So that matrix will then represent like the value which we can convert into a probability. And once we have converted to a probability, we can see whether the probability is say greater than 0.5, then we say the sentiment is positive. If it is less than 0.5, we say the sentiment is negative. So this is the simplest neural network approach for sentiment analysis. However, here what we are going to do is we are going to be using a recurrent neural network. Okay, so RNN. How does an RNN work? Well, basically, suppose you have a sentence which represents the review, and say that sentence has 10 words. Now, there is a technique which we use to convert each word into a fixed dimensional vector. So earlier we were designing the feature vector for the entire sentence. Now you can think that each word has its own vector. And then what we do is we pass these vectors to the neural network layer, which is the RNN layer, and we get we get the output embedding of that neural network. So whenever I say embedding, you can translate it as vector. So an embedding is basically a vector. So each word has an input embedding, and passing it to the RNN, we get an output embedding. And then that output embedding is passed through a fully connected layer or a linear layer, as I said, and that will be able to classify. So how do we exactly do this? Well, let's try to understand. Say this is how the RNN works. So as I said, every word, let's consider the entire sequence of words. Like here they're saying the sequence of words is x1 to xt, and then for each word we have an initial embedding which is small xt, and then when we pass it through the RNN, the way the RNN works is it generates the output embedding for the current word based on the input of the current word and the previous state's output. Okay, so you can see the mathematical formulation here. So ht is RNN of xt and ht minus 1. So that what this basically means is that at each point, at each word, we try to generate its output embedding by looking at the current word and the embedding we have generated so far, like of the previous word. So if we do it in a sequential fashion, you can understand that the output embedding at the very last word will sort of capture all the relations from the first word to the last. So H of capital T will represent the features of the entire sentence. So previously you were designing the feature vector for a sentence manually. What an RNN does is it generates that feature vector by sequentially processing all the words. So I guess there is a lot more details to RNNs and neural networks, but for now this much information should be enough. Okay, and as you can see, when we get the final hidden state, which is H of capital T, or the hidden state at the last word. Now what is a hidden state? By hidden state we mean the output embedding of the RNN. So the hidden state at the last word or the output embedding at the last word will represent the features of the entire sentence. And then we can feed it through a linear layer, also known as fully connected layer, to receive the predicted sentiment. Okay, so y hat is f of ht. So as you can see, they have given given a small example over here. So we have this sentence, I hate this film, and the input vectors or the initial vectors for every word is x1, x2, x3 and x4, and there is a initial h0 which we initialize randomly, or we can set it to 0, and then we can see h1 or the hidden state at word 1 or the output embedding at word 1 is generated by combining h0 and x1. Similarly, h2 is generated by combining h1 and x2 and so on. Finally, at the end, we get H4, and that is passed through this fully connected layer to get the final classification. All right. Now, one question you might have is that how do we get the input vectors? Like we have words, and how do we generate vectors out of words? Well, that is something we will see. But for now, you assume that each word has a vector, and then we pass it through the RNN to try to understand what the sequence of those words mean. All right. We will, I'll definitely explain step by step how we are generating those vectors and so on. But for now, this is the basic idea of how an RNN works. So you have a sentence, you have different words in that sentence. Each word has a vector to represent them, and we pass these vectors through the RNN. And after passing them through the RNN, we get an output vector at every time step. By time step, I mean every token. So at every token or every word, we get an output vector, and the output vector at the very last token can be considered to represent the entire sentence. And then we use that vector for classification. So generating that H4 is the duty of the RNN. Beyond that is what you would do for any other kind of module as well, where you get the final feature vector representing the entire sentence, and then you try to classify. All right. So, like, is there do you have any difficulty in understanding what I've discussed so far? If so, then I'll go over it once more. Otherwise, I'll go into the code to show you the details. All right, so let's jump into the code, and then we will see. Okay. So first step in any deep learning or machine learning task is preparing the data. All right. So here we will use a sub library of PyTorch, which is known as torch text. Now torch text is used to process text data for passing to the models. Like this RNN model, it has no idea of text. It takes vectors as input, right? A sequence of vectors is the input to the RNN, and it outputs a sequence of vectors. So from going to, like, when we have a sentence which is like a raw string, converting that string into the sequence of vectors is the data processing part. Then everything else is up to the model. Okay. So we will see how we do that. So first of all, this torch text library has a object known as field. Now what this field does is, suppose you have the initial data in the form of, say, a CSV file. Okay. So if you have a CSV file, then your text is like a string. So this field actually tells torch text how to process the string into the tokens. So like the job of the field is to take the string and divide it up into tokens or like individual words. Okay. And similarly, there is a label field which is used for processing the label given for the sentiment. Now, for tokenization, as you know, we can use different modules. There is NLTK and so on. But here we will be using Spacey. Okay. So Spacey is also like a language processing library which has a lot of features for different NLP tasks. So Spacey also has a tokenizer. We can use that for normal tasks. And if you do not, okay, so let's look at it first, then I'll tell you about the details. So the firstly we have to import PyTorch, import torch. Then because I'm doing this on Google Colab, torch text is not available by default on Colab, so we have to install torch text, and the code I'm using here is slightly old, so you will have to use this particular version of torch text, otherwise it won't work. Like according to how the code has been written. Now later versions of torch text, they have changed some things, so slight changes will occur if you use the latest versions. And if you want to use the code here as it is, you have to install this particular version, which is 0.10.0. Okay. So we install torch text and we use this data from torch text. Now you might be seeing two lines over here. One is manual seed and one is this backend. So these are not that much important. What this means is that like in deep learning experiments, we have this thing that like there are a lot of random things which are initialized randomly. Now if you do not set a seed every time you run the experiment, the values will be different, right? Because they are initialized randomly. But if we want them to be same, we have to use a specific seed, and then based on that, every time you run the same, every vector will be initialized in the same random way. Okay. And this statement actually further improves the deterministic capability of the model. So these are not that important, like you can just think of lines you have to just copy paste. Here is the important part. So here we are describing two fields, as I said. So first is a normal text field. We just use field for this, and we specify the tokenizer. So we use Spacey tokenizer. And like Spacey has different models, like different sizes. So this Encore Web SM stands for small. There are other models like large and transformer based models, but we are using the simplest one over here. So we have to specify it like this. And the label field, the field for the label, we are specifying that it will be a float, because it will be either 0 or 1. Okay, it will be either 0 or 1, but you can't keep it as an int. Most of the deep learning values, they require floats for calculating gradients and so on. So that is why we'll be using float. Okay, so let's run this. Okay, so sometimes you may see that because of this backward compatibility, this particular cell may crash. But even if it crashes, you can just go over here, restart runtime, and then run again, and then it will run. Okay. Next, let's come to the datasets. So TorchText has some facilities, like some common datasets are available on TorchText directly. Like you don't need to manually download them and then like read those files and do stuff. It's there given in TorchText, so you can use them directly. Okay, this line over here, like we are importing these data sets from TorchText, and we are taking the IMDb dataset, and this splits command that actually divides the dataset into train and test based on the default division given in the dataset. Like these datasets have some default split, and when we just call the function splits, it will return the train and test based on that default division. Okay. So if we run this, yeah, this takes a bit of time, so let it run. Let's discuss the next lines. So here what we do is, as you can see, we are dividing the data into train data and test data, and here we are just printing out the number of examples. So we will see this work. Now what they do is, they also show you how the data looks. Okay, so train data dot examples, so dot examples actually refer to the individual samples of data, and we are checking to see how the first sample looks like. So as you can see, we have used the Spacey tokenizer. Okay, so this one has run, we are running this one. So as you can see, this data set is by default split into 25,000 training examples and 25,000 test examples. Now, as you can see, because we have already called the tokenizer, after this processing, the text is already tokenized. So as you can see, this Elvira, Mistress of the Dark is one of my fab movies. It has everything you would want in a film and so on. There's a lot of things over here. Okay. So this is the entire comment which has been divided into tokens. And at the end, you will see this label, which is POS. So there are two labels in this dataset, POS and neg, for positive and negative sentiment. So as you can understand, each example from the dataset is stored in the form of a dictionary. So one key in the dictionary is text, which is like a list of words, and the other is label, which is the single string representing the label. Now, if you know, in deep learning, we usually have three kinds of dataset splits. So train and test is known. Like train part, we use it for training, and test is for checking the performance. But there is another data set we use which is known as validation data set. What is validation? Well, basically the idea is the test set is should be untouched. In no way should you use the test set for doing any kind of operations. The test set is just to, like, after you have trained the model and done everything, you run the trained model on the test set and you generate the final score. But you are not supposed to see the score on the test set and change stuff. Okay, so in deep learning we have these two kind of things. One are known as parameters. So parameters refer to, like, different matrices, vectors inside the model that get changed after training. So these are parameters. And apart from parameters, we have something known as hyperparameters. Hyperparameters are things that the experimenter or the user gets to decide. For example, what should be the rate of change, like learning rate, or how many epochs or how many passes over the entire data should the model be run. So these are called hyperparameters and these depend on the user. So the idea of the validation dataset is we check the performance on the validation dataset and we change the hyperparameters to get the best result on the validation set. And after getting the best result, that best model is used for getting the final performance on the test set. So validation dataset is used for controlling the hyperparameters. And it is, like, you might say we don't need the validation dataset, we can directly look at the test set and update the hyperparameters. But that is not very ethical because you might not always have a test set with you. Okay, so there might be some universal test set which is not shown to you. So in that case, you take your training set and divide it into train and validation, and test will be done completely separately, independent of everything else. Okay, so this data set IMDb, it has only train and test split. It does not have a validation split, but we need to create the validation split so that we can change the hyperparameters. So there's the split method. The previous one was splits. This is taking the default splits inside the data. But there is another method which is split. Okay, the split method actually divides whatever data you give it into the proportion you want. Okay, so there is also a parameter to this function which is split ratio that dictates what will be the ratio of documents in the two different sets. But by default this is 70/30. Okay, and this random state is for deciding which ones go to train and which ones go to validation and so on. So now we have train data, valid data, and test data. And let's look at the final statistics of the dataset. Okay, so as we can see, this is 17,500, 7,500 for validation, and 25,000 for test. I hope the screen is moving, right? Like you can see things change. Like, could someone just confirm?
Yes, sir.
Okay, okay. So now comes the next part, where is we have to build a vocabulary. So as I said, our input is string, or like the text is in form of string. We have to convert that string to vectors. So there is a process in between where we have to convert the string data into numerical data, right? So how that is done is we just one second. Yeah, so we have to build a vocabulary. What is a vocabulary? Well, vocabulary is like a list of words with a mapping to an index. Okay, so like we assign a numerical index to each word. We can choose which index we give to which word, it does not matter. Okay, so as our machine learning model only operates on numbers, each index actually is used to represent a one-hot vector. What is a one-hot vector? Well, suppose you have 20,000 words in your vocabulary and you assign indices 0 to 19,999 to 20,000 words. Then the one-hot vector actually is like a 20,000 dimension vector where it contains 0 for everything else and 1 in the place of the index which this word represents. So as you can see, I hate this film. The indices are 0, 1, 2 and 3, and if the vocabulary is only these 4 words, then the one-hot vectors look like this. Alright. Now, in our training set, there may be a lot of words. If we try to include all words, then our vocabulary will become very large and we won't be able to run our models. That is why we have to reduce the size of the vocabulary. And we can reduce the size of the vocabulary by either setting a minimum threshold. Say we say that every word has to occur at least x number of times to be considered in the vocabulary, and the other way is we sort the words by their frequency and we choose the top k words as the vocabulary, and every word that was not chosen in the vocabulary, we have an extra token in the vocabulary which is this UNK or unknown token, and every word that is not there in the vocabulary will be unknown. Alright. Apart from unknown, okay, so let's see how to build the vocabulary. So first we set the vocab size as 25,000. And it is necessary to understand that all these steps, building the vocabulary and all these things, has to be done only on the training data. We should definitely not use the test data, and it is advisable not to use the validation data set also, because we want the validation data to be a sort of like a test data for our experiments. Okay. And for the label will have a simpler vocabulary, like there are only 2 labels, pos and neg, and they will get 2 indices, say 0 and 1, like. Okay, so we use these statements to build the vocab. And then let's look at the number of unique tokens. So we had set the limit at 25,000. Now the number of tokens in the vocabulary is showing as 25,002. What is this 2? Well, one extra token is the UNK token, as we discussed. So 25,000 words. Apart from that, one token UNK to represent anything that is not there in the vocabulary. And the other one is a pad token. Now we need padding. Why do we need padding? Well, say we want to represent everything as a sequence of word indices, right? Like we are converting every word to an index. Now say we have 5 sentences which we want to pass to the model together. As you know, like in deep learning, usually we pass examples in batches instead of one by one, so that the model gets a better idea of how to update its parameters. Now the problem with text data is different examples may have different lengths of text. Say the first example has 10 words, the next one has 15 words, the third one has 8 words. So if we convert them into like sequence of word indices, then these sequences will be of different lengths. Ideally we want everything to be of same length, because that is how the matrices work in PyTorch. So what we can do is we can pad everything else to the maximum length. So the one that has 10 words, we have 10 unique words at the beginning, and after that we can insert 5 pad tokens. So the pad is basically just for maintaining sanity or like keeping the vector sizes consistent, but it should not add anything to the performance or decrease anything. All right. So like the example given here, say there are 2 sentences, I hate this film and this film sucks. So if we want to pass these 2 together as a same batch, then we have to add a pad token over here so that both of them have the same length. All right. So this is about the vocabulary, and here we are also seeing which words are most common. So as you can see, it's very understandable that these top words are very common. The, comma, dot, and a, of, to, so on. These are the common words. And then we will get other words later on. And similarly, you can see this is how the labels have been assigned. The indices of the words have been assigned. So UNK gets index 0, PAD gets index 1, and then the different words follow. And same for the labels. So neg gets index 0 and pos gets index 1. So at the end of this step, we have converted every textual thing into numbers. This is what we need, because these models do not understand strings, they only understand numbers. So we have converted everything to numbers. That is well and good. But then, how do we get the vectors of the words? We'll come to that. This final step over here is about creating the iterator. What is an iterator? It takes the entire data set and divides the data set into batches, and then it is responsible for creating the individual batches that can be fed directly to the model. Okay. So we have this bucket iterator. Like there are different kinds of iterators inside Torch text. But the bucket iterator, what it does is it groups sentences of similar length together so that the padding may be minimized as much as possible. Okay. So if you have to create multiple batches, it is best that the biggest sentences they go into one batch, the smallest sentences they go into one batch. So you are trying to group sentences having similar lengths together so that minimum padding is used. Okay. And this is how it is used. So we pass the three data and we specify the batch size. This batch size indicates how many examples should be passed together as a batch. So here we are saying 64 examples is one batch. And device is basically we are setting it to CUDA. Like if you don't know, CUDA means using the GPU. Like if you are doing on Google Colab, you can use it like this. But if you are using your own machine, then if you don't have a GPU, then it will be difficult. You will have to use the CPU, and that is very slow for these kind of models. So it is advisable to either run these models on Google Colab or on a machine which has a GPU. Okay. So we run this also. Okay. So next is the model part. Before I go into that, if you, like, do you have any doubts in this data building part? If you have, I'll just repeat that once again.
Excuse me, sir.
Yes.
Can we get the link for this code
Yeah.
access? Can we
Yeah.
access this code?
I'll give you not only the link for this code, but there is also a GitHub repository which contains some more more advanced things added on this. So then you can look at it on your own. So you will get all the
So
materials.
can you please paste that link in the chat box here?
Okay, just give me 1 second. So this is the GitHub repo, and they have a 6-part tutorial. I am just starting with the first part to give you a basic introduction into PyTorch for NLP and these kind of things. If you are interested, you can then look up the other parts on your own. Okay. And yeah, I know that.
Thank you, sir.
Yeah, and I know that it might be a bit intimidating to get into all these kind of concepts altogether at once. But the way I would suggest is that if you are interested in these kind of applications and all, some parts you will just have to mug up and start writing. Slowly, as you do more deep learning coding, you will get the hang of what individual things mean. So what I would suggest is try to get the overall idea what we are doing. Each and every individual line of code may not be understandable right at this moment, but the more you do it, you will get a feel of it. Okay. And it is also not possible for me to explain in that detail in a 1 hour session. So I am giving an overall idea or an overview of what different parts of the code does. uh, you can then look into individual parts in details yourselves. Okay. Now let us look at the main thing, which is building the model. Okay. So like in PyTorch, every model is like a subclass of this nn.module. So nn.module defined inside PyTorch is like the base class. We will have to inherit that class to create any model we want. And then we have to implement two functions inside the class of our model. One is the init, as you know, init for initializing. So over there we have to call the superclass initializer, and then we have to initialize every other thing which we are including in our model. And okay, let's look at a bit more depth. So there are three layers of, so each layer, by a layer I mean one module of a neural network. So there are three layers in this model. So at the very bottom is an embedding layer. What is this embedding layer? Well, this embedding layer is where that magic happens, that you pass the word index and it generates a vector for that word. Now, how does this magic happen? Well, the idea is for every word gets a randomly initialized vector at the beginning. And as we train the model, those vectors get updated such that they make the most sense for the given task. A bit abstract, but let me repeat once more. So you have an index for every word, or like a one hot vector for every word. Now that one hot vector, which is also known as a sparse vector, is converted into a standard dense vector using this embedding layer. And this embedding layer basically initializes every word with a random embedding. And then when you train the model, those embeddings get changed to reflect the nature of those words. So that happens automatically. You don't have to worry about that. That is the, like, the beauty of this thing. Okay. So let's see how this happens. So you have a one hot vector for every individual word that is passed to this embedding layer. That embedding layer generates a dense vector for every word. And then that dense vector is actually the xt. We were discussing for the RNN, there was an xt which is the input vector, and the ht's are the output vectors. So the input vector is created by the embedding layer, which is then passed to the RNN, and then it generates the output vector. Okay. Then, like, there are, as I said, you have to define, or you have to write down two functions inside any class which inherits the nn.module class. One is the init function, the other is this function known as forward. So the forward function is used to define how the data will flow across the layers. Okay. Now, as you know, in any neural network, there is a forward backward mechanism that we first, the model has some parameters. Based on those parameters, the inputs are processed to give some output. Then that output is checked with the actual output, and based on that, we do, like, some gradient calculation is done, and the parameters of the model are updated. So the forward pass is generating the output, the backward pass is like calculating the loss and passing the gradients back. So you don't need to worry about the backward part, you just need to worry about the forward part. PyTorch automatically does the backward thing for you. Okay. So you just need to try to understand how the data will flow across the layers to generate the final output. So from starting from this one odd vector for every word, how do we get to the final output for every example? That is what you need to bother about. If you get the final output, everything else PyTorch does for you. Okay. So so for each batch, now let's look at some, like, dimensions to understand how things are happening. So each batch like the text is a tensor. If you don't know, tensor is like a matrix, but it has this property of holding the gradients. Okay, so gradients are needed for changing the weights of the tensors. So for all purposes, you can assume that a tensor is a matrix.
Excuse me, sir. Can you tell me what is gradient in deep learning?
So gradient, as you know, like we do, like the way deep learning works is, so you have a model which is initialized randomly, and you pass an input through it to get an output. That output may be very wrong from the actual output. So like, as you know, in machine learning we have the input output pairs, right? So the output generated by your model may be very different from the actual output, and then you calculate what is the mistake I have made, which is known as the loss function. So there is a function which is called the loss function that calculates the difference between your predicted output and the actual output. Now, based on this loss function, the idea is that you have learned minima maxima in calculus, right? So the idea is we want to minimize that loss. So that is why we need to do a differentiation kind of. Okay, so that is the gradient calculation. So all these things are done by PyTorch itself.
Okay.
So you get a loss. Our idea is to minimize the loss. So we find out the gradients, because when the gradients are at zero, that is the point of minimum loss, right? That is the idea of maxima minima. So we calculate the gradients, and based on the gradients, the values of your model are changed. So that is one complete pass. The forward pass is you are generating your output, and the backward pass is those gradients are flowing back into the model to get the, like, to change the model's values such that the next time you pass the data, the loss will be smaller. That is the concept.
Oh, gradients means to avoid the errors or mistakes or deviations from
Yes, yes,
the
yes.
training data.
Yes, yes. Now the deviation from training data is the loss, and gradients are used to calculate that by how much should we change our values so that the loss gets minimized. Right.
Okay.
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 So that is about gradient. Now let's look at the how the matrices look. So one thing about deep learning is the most important concept is about understanding the different size of the matrices, because that will guide you in writing your code. So at every point of time you should have an idea that what is the in like what is the matrix size that you are passing to a current operation, and what is the output matrix size. So let's look at this. So uh, each batch, each batch is a tensor of size, like batch size. So suppose we have 64 examples, so, and sentence length. So suppose we have 64 examples and the maximum length is 100. So as I said, we have padded all examples to 100 length. So then our input is 100 cross 64. Okay. Now we were talking about one hot vectors. So if they are one hot vectors, ideally the input should be like 100 cross 64 cross 25,002. But we don't have the 25,002 because PyTorch deals with that automatically. So you give the index, PyTorch automatically creates that one hot vector, which is then passed to the embedding layer in the later stage. Okay. So at the very beginning, the input is of this shape: sentence length cross batch size. Some people do it in the other way also, like you can have batch size cross sentence length. So some changes have to be made in the model to keep it like that. It's a matter of convenience, which way you want to look at the data. When your input batch is passed through the embedding layer, so what this basically means is that you have 100 cross 64. So 100 words per 64 examples. Now, when we give the embedding for each word, so embedding for each word means like a vector for each word. So here this matrix, every element in this matrix represents a word. So when each word itself becomes a vector, so then the matrix shape changes to sentence length cross batch size cross embedding dimension. Embedding dimension is the length of the vector which is given by the embedding layer. That is something you get to choose. Okay. But basically this dense vector, right? So this dense vector, the length of that, the dimension of that is the last value over here. So this is the output of the embedding layer, which will be passed as input to the RNN layer. Now the RNN layer returns two tensors. One is of size same as this. So this is like the output embedding at each word. This represents input embedding at each word. This one represents output embedding at each word. Like as I said, if you see this diagram once again, we have an input embedding at each word and we get an output embedding at each word. And the final one over here is the one we are interested in, right? So that is given directly as well. So the RNN returns two different matrices or two different outputs. One is this output embedding at every word, and the other is this hidden, which is basically the hidden state from every time. The hidden state at the last time step. So if you have in a batch, if you have 100 words, then the 100th word embedding that is returned through this. So basically this is extra. You can extract that part out from here itself, but it is given for convenience. Okay. So hidden is simply the final hidden state, and you can actually check that if we extract the final, like the hidden state at the last time step, if we extract that from here, then that will be equal to this one. That you can check manually. So let's see how we write the code for this. Well, as I said, we have to inherit the nn.module class. Then we have to define an init function. First we call the init of the super. Then we define those three layers. First is the embedding layer. As you can see, we have input dimension and embedding dimension. So input dimension is basically the size of the vocabulary, and embedding dimension is something you get to choose. Then RNN, that has the input dimension is the embedding dimension and output is the hidden dimension. You can keep them same, you can keep them different, all up to you. And then this FC or the fully connected layer is the layer at the end where you pass the hidden dimension as input and the output dimension for this task will actually be 1. As I said, here we are going to generate a single output for every example that will give a value which will convert to a probability, and then we will decide if it is positive or negative based on whether the probability is greater than 0.5 or less. Alright, so this is how you define the layers. So the init function is used for defining the layers. Now the forward function, as I said, is used for defining how the data will flow. So you have text as your input. As we said, text is sentence length cross batch size. Then we pass it through the embedding, self.embedding layer, and that the output of that has this size. So the embedding dimension gets here. So every word which was initially a single index has now been converted into a vector. Okay. Then we just pass it directly to the RNN, self.rnn embedded, and we get these two outputs as we discussed. So output is sentence length cross batch size cross hidden dimension, and hidden is 1 cross batch size cross hidden dimension. And as I said, we can check that they are equal. So we are taking the last token of the output. So sentence length, this axis represents the individual words for every sentence, and here we take the very last word and we compare it with hidden. Now this squeeze 0, squeeze is used for removing any axis which has a dimensionality of 1. So as this one is 1 cross batch size cross hidden dimension, we can make it as batch size cross hidden dimension by using the squeeze function. Okay. Similarly, as I said, your output will be of the form like hidden, this hidden because the hidden is in this form, we have to squeeze the hidden when we pass to the final fully connected layer, and that we are doing over here. Okay, so this is the model part is very simple, like very simple compared to other libraries like TensorFlow and all. You just have to understand how the data flows across the layers, and you have to just write that down. Everything else will be handled by PyTorch. Okay, so we do this. Now we have defined the model, we have defined the data processing. It's just about calling them. So let us initialize the model. So here we are specifying. So input dimension, as I said, that is the vocabulary size. Embedding dimension we get to choose, that has been set as 100. Hidden dimension again we get to choose, decided as 256. Output dimension depends on number of classes in your task. In this task we have just one class, like two classes, but they are 0 and 1, so that is effectively one class, and based on that value we will just decide on a threshold whether it is the positive class or negative class. Okay, and we initialize our model. Now this is just for seeing how many parameters our model has. So even this simple, very simple model has 2 million parameters. So that is the caveat of deep learning. Models are huge. So the most simplistic model also has 2.5 million parameters. Okay. Now training. So firstly is this concept of optimizer. What is the optimizer? The optimizer is a module which is used for calculating the gradients. As I said, we have to calculate gradients and flow them backwards into the model. So the optimizer is used for these. Optimizer is used for updating the model with the gradients. So you calculate gradients and you have to change the model's parameters in such a way that the loss gets minimized. That is based on the gradients. So that is done using this optimizer. There are theoretical explanations to all of this, but we are not going into all that right now. And as you can see, this is this parameter learning rate. Learning rate basically defines how fast your model will learn, or how by what factor should the parameters be changed at every step. Now if you keep this too high, the values will change very rapidly and the model won't be able to learn. If you keep this too low, then the model will learn very slowly, like very small changes will be made at every step. So then again it will take a lot of time and it may not learn. So deciding on a perfect learning rate is like a hyperparameter choice. So that is the job of the user to determine what should be the ideal learning rate. And as I said, we have a loss function. Okay, so there are different loss functions in deep learning. What you need to know right now is, because we are using like binary classification, right? We are doing either 0 or 1 classification. So that is why we use this BCE with logits loss. It's a big name. You don't need to understand the entire thing. Just know that when we are doing binary classification, we have to use this loss function. Okay. And finally, all of them are being moved to GPU. So device was decided in previously, and that has been done over here. And finally, this is like calculating the metrics. So you have predictions and you have the gold standard Y. So you take every prediction, and this torch.sigmoid, what it does is, it given any value, it converts the value to something between 0 and 1. So a probability. It converts every value to a probability. So there is a mathematical function which is used for doing this. You pass any input and it will give an output in the range of 0 to 1. So that is the job of this sigmoid function. And then we just check whether they are equal to y or not. Okay. And the accuracy is like we sum up the total amount, like number of correct ones by total number of predictions. All right. Now we have to understand that the model can be run in two modes. One is the training mode and the other is the evaluation mode. What are the differences? Well, there are a lot of things, like we do some specific things such as dropout and normalization. These are advanced concepts. So those things only happen during training. Okay. Uh, Now as you can see over here, like this description is pretty detailed. If you look into it later, you will be able to understand more clearly. So we have to call the model dot forward which with batch dot text, but we don't need to specifically write it like this. If we just say model then bracket open bracket close, that means we are calling the forward function of model. That is how it is defined in PyTorch. So usually what we will do is, instead of calling forward explicitly, we'll just give model bracket open and we'll give the inputs, and automatically the forward function will be called. And okay, let's look at what happens over here. So this is a function which is written to do one training pass over the entire data. Okay, so we like one single pass. So one single pass over the data is known as an epoch. Okay, so we have an epoch loss and we have an epoch accuracy, and we will pass the entire data in batches to the model. Okay, so we have already defined the iterator which will generate the batches. So we call each batch. So for batch in iterator, okay. Firstly, we have to, whatever gradients have been accumulated in the optimizer has to be cleared out. So we clear that using this function 0grad. Then we call model batch.text, and then we squeeze it. Why? Because the predictions, as I said, in this case the output is one dimensional, right? So suppose if you have batch size of 100, then the output given by model will be 100 cross 1. So we don't need cross 1, we can keep it just 100. That is why we are doing squeeze. And the gold standard labels are also like you have 100 values, simply 100 values. So that is why we have to squeeze this. Otherwise this loss function will not work. So we calculate the loss by calling them directly on this. So predictions is what your model is returning, and batch.label is the gold standard. That is the loss. And simultaneously we are also calculating the metrics, which is the accuracy. We are calling that binary accuracy function using the same things. Now this loss, whatever you got, that is also a tensor. Now herein comes the main part of deep learning, whereas we call the backward function. What this backward function does is it calculates the gradients, and optimizer.step updates the model parameters based on the gradients. So these are the two steps that actually trains the model. So as I said, you have a model with some parameters, you pass the input, get the output, you calculate the loss, then you calculate the gradients based on the loss, and then you update the model parameters based on those gradients. Okay, so you don't like everything else is linked with them. So loss dot backward actually updates the gradient values inside the model itself, and optimizer has been initialized with the model. If you remember, the optimizer is initialized with the model, so the optimizer already knows what the gradients are, and so we can call it directly. That is why there are no inputs to these functions. And finally, because these are tensors, to convert them directly to float, so these are tensors but like unit tensors. So like just a single value which is has been represented as a tensor, we can get a direct float from it. So we call the item function to get the float, and at the end of this process we are returning the average loss and the average like accuracy. Okay, so this is for training the model. When you evaluate, all the steps will remain same, except we won't need optimizer anymore, we won't need to call loss.backward, and we won't need to call optimizer.step. So these three lines will be removed when we do evaluation. So as you can see, they have now written a different function for evaluation. Over here everything else is same, just those three steps are not there, because we won't be doing any changes to the model when we are evaluating. All changes will happen only during training. Okay, and the main difference is here we put the model in training mode, here we have to put the model in evaluation mode. Okay, Finally, this is a small function just for calculating the time. Okay, so this is done. Now everything is ready. We just need to call this train function and this evaluate function on the data one by one. So every epoch is like a single pass over the data. So you pass, like you call the training function and then you call the evaluation function, and that completes one epoch. And we decide how many epochs we want to run the model. So say we have decided 5 epochs. Okay, and we have to keep track as to in which epoch the best performance was achieved, because that model will be later saved for every purpose. So the idea is the more epochs you do, the model gets more trained, but sometimes there may be aberrations. That is why we have to keep track at which epoch we got the best value. So as you can see there, this is like for every epoch they're calculating the time over here. The main part is over here. The train loss and train accuracy are calculated by calling the train function. Similarly, validation loss and accuracy calculated by calling the evaluate function. And if the current loss is less than the best loss, then this is the best loss and this is the best model. That is the idea. And we print all the details at the end of every epoch. So not much in this function. It's just about calling those main functions and running them. So now this takes a bit of time. This is a very simple model and a very simple data. That is why it will still run fast. But if you do deep learning, you will understand that different models take different time. Some will take more time and so on. So here it is taking 15 seconds for every epoch. And you will see that multiple epochs will be done in this fashion. So as you can see, the epochs are getting calculated. Now the idea is as you run more epochs, like the training loss should, like the losses should decrease and the accuracy should increase. That is the general idea. But over here, we have chosen a very simple model, which is quite limited. And that is why we are not seeing much difference, but everything is working correctly. We are, however, not seeing very good values, 50% accuracy only. So that is because the model over here is very limited. When we choose better models, when we use more efficient tips and tricks, then we will get better values. Okay. But the main thing is the model is running. So as you see, 5 epochs have been completed. And at the end, you have to check the test result. So this is getting calculated on the validation dataset. So we now have a final test dataset. So as you see over here, we have saved the model using this command. Here we load the saved model, and then we call the evaluate function, but this time with the test dataset, not the validation dataset. And this gives us the test results, which is not very good, 47.4. Okay, so you can make more, like I gave the link to the GitHub. So if you look at that GitHub repo, they have 6 tutorials on sentiment analysis. So this is the very first one, and it is the most simple one. This is just an introduction into PyTorch and how to use PyTorch for sentiment analysis. So because we are out of time, I won't be able to cover the second part. But if you have a look at it, it's detailed over there. And if you run that second part, you will see that you will get much higher accuracy, because that uses a more powerful model, which is known as LSTM. It is a more powerful version of the simple RNN. And they use other tips and tricks which are needed for improving model performance. All right. So, okay. So any doubts in this part which I covered since the model? Okay, so somebody had asked questions. I did not look at this part. RNN model is most suitable model for sentiment analysis. Well, no, RNN is the most basic model. There are advanced variants of RNN which are known as LSTMs that will do better. Then there are even more powerful architectures such as transformers and all. They do even better. So no, and your second question is marks in the final questions in the final exam. In the final exam, there will not be any programming. This is for your understanding of how to practically do the tasks which you are being uh, shown or taught in the lectures. Okay. And as to the type of questions you will have, I think it is better to ask the course TS because we do not have any idea about that. We are just for showing you tutorials and like hands-on sessions. So, yeah, but definitely you won't be having any programming type questions that I can say because the questions you will have will be more or less based on the kind of assignments and all you are doing. This is slightly different, as in I am showing you a hands-on session as to how to do these things practically. But in your exams, you won't have these things. Okay. Okay. So, any more doubts? Yeah, this is practical. This is like not part of your syllabus per se because as you understand RNA and LSTMs, these are pretty advanced concepts. Deep learning itself is a course of its own. So we are just giving you a flavor of how to do these things if you do want to like do projects on NLP and all that. Okay. So I guess we are done for today. Um, yeah, I'll upload the first and second parts. I could not cover the second part, but I'll upload that PDF. And apart from that, you can access this link to get a detailed analysis of or like even more advanced concepts if you want. But for to start off, this first notebook and the second part should be enough. All right. Okay. Thank you then. We'll end the session today here itself. Okay. Goodbye.